afternoon, depending on who you are, and Happy New Year. Welcome to the first seminar in the virtual seminar series that is put together by the Chemistry Education Division. Today's talk is going to look into how augmented reality is used to visualize chemical entities. This topic came in response to an interest in active learning that the community expressed during a survey that took place sometimes in the summer last year. Today's speaker comes to you from University of Victoria, Professor Scott McIndoe. He's a full professor at UVic, and myself, Violeta Ayuso, who I'm just an assistant teaching professor at UVic at the same institution. In terms of the structure of this talk, Scott is going to start you on the journey that led to the app. It's called Molecular. That's going to be basically the center of this talk. He's going to talk about the implementation of Molecular in the course he teaches, Chem 101, basically the first chemistry course students see when they come to UVic. And then I'll take over for a little bit to talk about how Molecular looked like in the introductory organic chemistry class that I teach. And then I'll pass it back to Scott so he can share with you the results of the survey that we presented to the students, basically the first week this year. Okay, so basically that's what the feedback from the students comes from. Feel free to type questions in the chat while either one of us is talking. We'll take turns in trying to answer the questions in the chat. If that's not a possibility, for example, if I do not know the answer to a question, we'll wait until the talk is over and we'll answer those questions individually. I'll ask Scott to answer the question I couldn't answer, for example. Right, so let me tell you a little bit about Scott. He grew up in New Zealand. He completed his PhD in organometallic chemistry at the University of Waikato. His research interests are multiple. He looks into organometallic catalysis and synthesis. I know him more as a mass spectrometry chemist, where he is building this very interesting techniques to look at reactions in real time. I'm an organic chemist, so catalytic cycles and they look nice, but I wouldn't want to be involved in the process of discovering one. But the tools Scott is building are quite amenable to doing that. He's also interested in methods and ways of getting the students in this large enrollment first year courses that he teaches engaged and enthused about learning. So a lot of the research into teaching that he's doing is centered on this idea of getting students excited about chemistry. Scott has multiple awards, both in research, for research and teaching, but I'll mention only the most recent one, and that is that he became the 3M National Teaching Fellow in 2022. So that's it. With that being said, please join me in welcoming Scott to our seminar.
All right, thank you, Violeta. So today I am going to be talking about our journey towards developing an augmented reality app. And hopefully for those of you who have devices handy, you might have looked at the screen that was in front of you and followed these instructions here. That QR code leads to the Apple Store. So if you have an iPhone, you would be taken directly to download that app. It's free, it's safe, and I'd encourage you to do it because there's a part later in the presentation where you'll be able to use that app yourself and sort of see it in action and see how it works. As Violeta said, I teach first year chemistry. These are large classes. We have about 900 students in first year at UVic in classes, section sizes of about 350. So getting them involved in active learning is a perennial challenge. And one of the things that we encountered very early on, well, I should say I encountered, and I'm sure other people have as well, is that chemistry is very much a 3D subject, but it is also predominantly taught in 2 dimensions. So we use textbooks and presentations on the board and slideshows and things like that. These are all 2D representations, and we can kind of get around it a little bit by showing them video, but really we would love to be able to get them as hands-on with chemistry as early as possible. And it is certainly true that often these 2D representations of 3D objects can be confusing when you first encounter them. So I've just collected here 7 different depictions of an octahedron, for example. And if you're experienced in chemistry, you can look at all of these and instantly see what it's depicting, but it's much more challenging for students who are new to the subject and are not yet able to lift that representation off the page and into a 3-dimensional format in their mind where they can rotate that around. And so some of my early ideas about how to get around this sort of centered around the lab. I was really intrigued about 10 years ago when a technology called a 3D printing pen came out, where you could just like sit there and draw in 3 dimensions. And I thought, oh, this would be great. Rather than drawing a molecule on a piece of paper, maybe they could draw a molecule in 3 dimensions and then pick it up and turn it around. And so we got a bunch of these pens, and I got a bunch of student volunteers from my first year class to come and try them out. And you can see them all using them here. Essentially, a 3D printing pen is a pretty simple device. It's basically just the printing head of a 3D printer, and your arm is the XYZ. So you just move it around, and the plastic gets extruded from the tip of the pen. And you can see them all here to varying degrees of success, making molecular structures. And so we, of course, like surveyed them afterwards and tried to figure out what they thought of this whole process. We got some positive feedback. They said it was very helpful to draw the molecules and make them into the molecular shapes. It was easy to conceptualize and so on. Someone else said they thought it was a very interesting and engaging way to learn about molecules. So that was very positive and kind and all the rest of it. But what was really far too kind, given that that session was something of a disaster. And this student gave a much more honest appraisal of how that worked out. So they said, my experience with the pen was that it was slow going and unintuitive. It took a lot of time for little reward. We had 10 pens in that session, and I think 3 of them broke. It was incredibly slow. Many of the molecules just looked like plastic spaghetti. And so we pretty much resolved to abandon that idea in the very early stages. However, the grad student who was working on that project, Natalie, was fantastically good at using these 3D printing pens. And so we wrote up an article anyway, and you can see that she created some really nice shapes. So one of the things that we found is that it was much easier to make the shapes if you templated them. So we provided the students with these silhouettes of parts of the molecule, and they could fit them together after they'd sort of drawn them in 2 dimensions and make a 3-dimensional object, and then just sort of glue them together, as you can see Natalie is doing there. But pretty soon after that, we realized, well, maybe we should just be giving them the physical templates themselves, and they can just like join them together and make a 3-dimensional object. And so the next thing we did was to make these acrylic models. So all the templates essentially would be laser cut ahead of time, and they could fit them together to make these 3-dimensional models of the molecules that we wanted them to understand. And so you can see that every molecule that we have, we can make out of just two pieces of acrylic. And again, we published this a few years ago, showing that you can, all these patterns are available freely for you to download, so you can cut these things out for your own students. So the idea was I was principally using this to teach VSEPR theory. And so I basically made a model kit that contained 26 parts, so we could make the 13 sort of fundamental shapes that you see in VSEPR. And back in 2019, these costs, we could make them for about $5 per kit, but it became exorbitantly expensive once COVID broke out because the price of acrylic went through the roof and the availability of acrylic plummeted. So we had to look to other ideas for producing these things. And so the availability of all sorts of sheet goods during COVID was not great. And so we ended up making them out of cardboard. This had the virtue of that we could just slip these pieces of cardboard into the lecture books that the students buy themselves for Chem 101. And we could then get 13 geometries just in one color now. Though you could, of course, color them yourself if you wanted to, for about 25 cents per kit. So this was much more affordable, but also kind of less satisfying, in that you can see that the cardboard is not the strongest material ever, even if it's sort of a thick sort of cardstock like this. And it was pretty easy to sort of smush the models, not only when you were making them, but when you were handling them as well. So they were really too fragile. And so in the coming year, we're probably going to move back to a plywood model. So acrylic is still too expensive really to make 1,000 sets of these, but we're going to make some instead out of plywood, which is pretty inexpensive and can still be produced in a single sheet that can be included with the lecture book. And we don't charge the students for this because the cost is pretty minimal per student. Around about that time, one of my grad students, Anuj Joshi here, he was telling me about an amazing experience he'd had in the department with an undergrad student who had built a virtual reality setup to interact with molecules. And so this, of course, is in 3D and in virtual reality. And Anuj was very taken with this experience and insisted that I really had to talk to Julia, the undergraduate who was involved in making this particular thing. Now, virtual reality is not a very accessible technology. It requires everyone who's using it to have a VR headset. And so I was more interested in sort of augmented reality, which is much more accessible in the sense that just about every student has access to a phone. So this is Julia. She is the 2023 BC Rhodes Scholar-elect, so a really outstanding student, very talented, and she did all of the hard work in building this app from the ground up. So what is augmented reality? All of you have encountered this, of course. Anytime you use a filter on your phone, you are using augmented reality. It's basically adding digital content to what you're seeing on in your phone's camera. So over here we have this is the augmented reality game. Pokemon Go has AR technology in it, where the Pokemon can be running around in the environment that you're using. For anyone who has struggled with choosing, excuse me, the perfect IKEA furniture for their home, IKEA has an augmented reality app where you can pull out your phone or your device and point it at your room and then populate it with various IKEA furniture to see what it would look like in situ. There's all sorts of fun applications. There's an app called Ink Hunter where you draw 3 lines on part of your body and then you choose a tattoo, and then the augmented reality technology will project that tattoo onto you so you can see what you would look like with that tattoo before you go to the expense and pain of having it permanently etched onto your body. So molecular, and I think this is once again, this is the link to the iOS app. And so what I would like all of you to do, and ideally this would be interactive. So if you can possibly download this app, that would be great. This is just for the iOS. So if you want to, I mean, the QR code is for iOS. So if you have an Android device, please go to the Play Store and search for molecular. And you should see an icon that looks something like this thing on the left-hand side here. I will demonstrate the app for you. I'll show you some video recordings, but it's really not quite the same as getting hands-on with the app and actually using it. So I encourage you to do that if you possibly can. So there are, of course, many augmented reality apps that allow you to look at molecules. One of our top priorities was to link the augmented reality aspect of the app to our own lecture books. And so the idea is like what we're asking the students to do is to try and imagine that object popping off the page into 3 dimensions. And we're kind of, we want them to do that, be able to do that in their mind. And so what the augmented reality can do is kind of scaffold that process. It helps them see the object that is printed in their lecture book in 2 dimensions. It then just pops off the page, floats above their lecture book, and they can interact with it. And you can play around with that object. You can't, of course, see my fingers working here, but I am actually rotating by pointing at the screen and dragging. So you can turn it around. You can zoom by pinch zooming. And you can drag the object around by using multiple fingers to drag. Okay, so what I would really like you to do now, and I'm hopeful that at least some of you now have the molecular app, to try and use it on the screen here. Now, the QR codes on the screen here are not, they're designed to be printed at a specific size in a lecture book. So they look something like this in the lecture book. I'll have to put that upside right down. So it looks something like that in the lecture book. These, of course, are just projected on a screen in front of you. So what you may have to do when you're using the app is to play around with the distance you are from the screen. So I find if I'm successfully using it now, what you might find is you're like far too close to the object and it might appear as like this enormous thing 3 feet high right in front of you, or you might find it to be quite tiny. But you can, of course, zoom in and out using a pinch zoom, and you can rotate it around as with most augmented reality things. There's 2 different types of 3-dimensional object here. And in Chem 101, the main sort of very unfamiliar 3-dimensional objects that we want them to understand are orbitals, which are very complicated looking things that, if you haven't seen them before, successfully recognizing them and understanding them is really quite tricky. So we have a bunch of QR codes for all the different types of orbital that we want them to have an appreciation of. And then we also have QR codes for each of the fundamental VSEPR shapes, which we want them to understand as well. So linear and trigonal planar and tetrahedral, trigonal bipyramidal, octahedral, and all the ones with that are generated from those 5 fundamental shapes. So, yeah, I mean, I can't, of course, interact with you interacting with this thing, but I hope that you're having some enjoyment out of it. If you would like to use it again afterwards, what I would encourage you to do is to take a screenshot of these QR codes, and then you can print them out or use them later on if you want to try it later, because the app does require there to be a QR code for it to interpret, because it's designed to be fixed in a certain point in space. Okay, so we have surveyed the students and their experience in using the app. And we did this really quite recently, actually. So the first full rollout of molecular happened in the fall term of 2022. We rolled it out to the 900 or so Chem 101 students, and Violetta and Dave Leach rolled it out to the 200, actually there may be about 600 students in Chem 231. So we asked all of those students earlier this year, in the first week of January, some questions about their experience with the app. And we got it's definitely a less than 10% response rate, but of course the survey has to be optional and voluntary. And so that was I think we feel like that's given us good enough statistics to sort of understand their experience with the app. Not too surprisingly, most of those who bothered to do the survey had also used Molecular. So about 85% of them had used the app, which was obviously encouraging for us. We did want them to use it. And keeping it free, of course, helps lower the barrier substantially for use. So we were really not too sure what would happen in terms of how useful they had found it. But the vast majority of those who had used the app did find it very helpful, or at least somewhat helpful, in the understanding of the 3D shapes of molecules. We got a very, very similar distribution when we asked them about the 3D shapes of orbitals as well. So they were essentially really the same question. It was equally helpful for orbitals as it was for molecules. So there's no real distinction between the type of three-dimensional object that they're trying to understand. The augmented reality was helping them. Some of them, of course, strongly disagreed that it helped their understanding, but Chem 101 sort of has a fairly substantial failure rate. So I'm sure that for some of those students that was probably true. It didn't really help them enough to get them through the course. But overall, very positive impressions of the app itself. They nearly all found it easy to use as well, which is obviously a priority. We want them to be able to just whip it out in class while they're being taught about a particular three-dimensional object and interact with it essentially on the spot. And so making it easy to use was a priority, and I think we had successfully achieved that end. We also asked them for feedback on their experience. Lots of very positive comments. So they said an excellent addition to the teaching team, very cool and fun to use. They aided some really nice comments here, like where it aided in my understanding where the textbook and other tools confused me. And that's really what we wanted to do. We don't anticipate an augmented reality molecular viewing app to be the be all and end all. What we wanted to do is to help those who are struggling with the other representations of molecules, be them physical or in the lecture slides or in their textbook. We want to help them, provide them with another tool where they can that can help them with their understanding. It was massively useful in connecting to the drawings they'd seen in the books to a more real world setting. I mean, I guess that's sort of, real world is certainly just like more getting hands-on with the orbitals and the molecules. This was by far my favorite comment though. Someone said it was surprisingly good. And that was great in the sense that, often when you're excited about a new tool that you've got for students, you kind of hype it up. And clearly there was a healthy level of skepticism in my class that this was going to be anything like as good as I said it was. So the fact that someone found it actually helpful and good was very gratifying. By far away my favorite comment. We also got a ton actually of feedback about how we could make it better. And one of the things that was interesting to us is that in just about all the augmented reality apps that are out there already, they don't tend to be tied to a QR code. They can just like download any molecule and play with it in augmented reality. And we thought like tying it to the lecture book was, a key aspect that we wanted to have. So, this idea of object popping off the page into 3 dimensions. But a lot of them actually wanted the facility to play around with the molecules without worrying about that. So the sort of more conventional way of just projecting a molecule on your screen and being able to interrogate it yourself was obviously a priority. So we're going to have to make a decision soon about whether we just point them to another augmented reality app or some other resource for this, or actually incorporate it in the app itself. And that's going to depend on how we develop this with Julia going forward. There was some feedback which said like it's sometimes a little bit wonky. They didn't like it, the molecules are on a timer. So basically they get projected above the page, but they don't stay there forever. They disappear after a little while, sort of amount of time that we judged was enough for them to interact. They wanted things like to be able to search for molecules. So rather than just like search for a QR code in their book, they could have a menu where they could pull that down and find out what molecules are out there. And they also wanted to be able to look at reactions, showing the 2 things coming together to form products and so on, in order to understand the reactions as well as the molecules. So that's a cool idea, and one we hope to implement as well. Okay, so I'm trying to give myself plenty of time here so that Violetta has time to talk about her experience in Chem 231, but also I'm keen to have feedback at the end of the talk. So I'd just like to say a huge thank you to Julia, whose sort of talents with app creation and understanding sort of the world of molecular interpretation, and it has been a wonderful asset in this thing. We absolutely couldn't have done it without it. Thanks very much also to Dave Leach, who is Violetta's teaching partner in Chem 231. He has also incorporated this into his lessons as well. I've been very lucky over the years to have help from the University of Victoria's Learning and Teaching Support and Innovation, and the Department of Chemistry has been great as well. Like the Chem 101 has enough students coming through it that even sort of small additions to the program, small innovations, can have a fairly substantial impact if you multiply them over all of the students that are in that course. So it's certainly a place where innovation is encouraged and fostered. And so with that, I'd like to pass over to Violetta, and she will tell you about the use of the app in Chem 231.
Thank you, Scott. If you stop sharing, then I'll try to share.
Mm-hmm.
See my PowerPoint presentation. All right. Okay. So I was hoping that Scott was going to share with the results of the survey after I had talked about this, but now, the secret is out. So I basically, my
I should have given a spoiler alert to that. Sorry,
yeah,
Viola.
that's fine. It's just now you get to see the what caused those types of answers in the surveys. So in terms of my portion of this presentation, I'm going to go very slowly through some of the examples that we use molecular for in 231. So when it comes to the course itself, like the course that we implemented molecular in, that's Chem 231. It's the first organic chemistry course students take at UVic. Last semester, the class size was 450 students. That's a typical size for this class, and the prerequisite is the course Scott just talked about, Chem 101, Fundamentals of Chemistry. So when it came to molecular in organic chemistry, we wanted this, by the virtue of the tool, it's an active learning tool that could ideally promote student engagement during class, because I would give them time to, project the molecule and look a little bit at the molecule during class time, and ideally out of class or after class. And they, the informal feedback that I received was that they used it after class. The app was meant to complement what was already part of the course design. That is our lecture book. And basically the lecture book is a repository for the content and the way we approach organic chemistry, teaching organic chemistry, I should say. And most importantly, we emphasize the molecular models all the time. So we wanted the app to kind of complement, not substitute, the molecular models. So that was the plan. So when we were thinking about this, I was wondering, I stopped and asked myself, what can this app help me and the students with? So some of the things that came to mind would be visualizing lone pairs. We do have a hard time with visualizing those lone pairs, especially when they are involved in resonance or when they are not involved in resonance. It's very often that students would want to delocalize the electrons that are in an sp2 orbital, for example. So hoping that they can see where the lone pair was, we thought that particular misunderstanding would be eliminated. When it comes to symmetrical molecules, for students to predict or to be able to understand the NMR spectra, it was a good way for them to see, what makes a molecule symmetrical, and as a result, identify the number of types of unique hydrogens or carbons. Visualizing orbitals, so we don't talk a lot of orbitals in Chem 231, but when it comes to the structure of double bonds and triple bonds, I think if they can see those, pi systems and their perpendicular relationships relative to the sigma framework and so on, that would help with reactivity later on. We wanted to look into types of stereoisomers, enantiomers, diastereomers, and meso compounds. I think with meso compounds, it's a little bit more, they become a little bit more accessible once you have them on the app, but with enantiomers and diastereomers, we need to work a little bit at that. And you probably saw there was an earlier comment referring to stereoisomers in Chem 231, how they disappeared before the student had time to compare and contrast them. Another application of the app would have been reactive conformations, especially in E2 eliminations for substituted cyclohexanes. And last but not least would be, molecular complexity. So give the students a way to appreciate how complex an organic molecule can be. And the example we chose was doxorubicin. We used this as a question on one of our midterms. So here is, so in what comes, I'll have an example of each of those intentions of ours. In some cases, I have screenshots. After this, I have a short video. Hopefully that is going to work well. So when it comes to lone pairs, this is one example where nicotine has two nitrogens, different hybridization. And I played with the molecule until I took this screenshot where you can see the lone pairs. So if you'd like to try the QR code, I can wait a few seconds and you can actually see how it works. Seems to be a pretty busy molecule, but I like this example because of that idea of an sp3 nitrogen and an sp2 nitrogen in one structure. Is it working? Perfect. Yes. I did have a little bit of fun yesterday trying to put this presentation together. I wasn't, unlike the student that was surprised by how good it was. I was surprised by how much fun I had, to be honest. So this is one example where lone pairs, can become visible. You can actually see them. This is that idea of looking into unique hydrogens or carbons. So here I have a tiny recording of my screen. So this is me playing with that particular structure. So see, this is part of a practice problem set, and they can this is a chance for them to identify primary, secondary, tertiary carbons, and also the symmetry within the molecule. So it's I don't know. I think it's it really helps, with visualizing, the symmetry of a molecule. Right, and then I have an example. Okay, oh, this is my next slide, right? Give me a second. Yes, this is where orbitals are the focus of the application. So this is, from the lecture book, we have an attempt at describing orbitals, the pi bond and the sigma framework, but then with the app, we can actually see, right, the perpendicular relationship between the two of them. And this is one of those concepts that I have difficulty explaining to students. And, to be honest, this app also helps me convey information very clearly. It's not only them, playing with the structure, it's also me making myself better understood when teaching or while teaching. And then this is that idea of, stereoisomer. So this is a meso compound, for example. And this is also a little bit of a video when you can play with the QR code. But if you don't want to, you can watch me playing with it. So we try to emphasize the idea of a plane of symmetry when it comes to meso compounds, and that's what the app helps with. I sometimes forget that you can zoom in or out. So when I remember that, I play with that function, and I think this is one of those examples. We're looking into the reactive conformation for a particular reaction, right? So when we talk E2 eliminations, we're mentioning we have to talk about that anticoplanar relationship between the leaving group and the hydrogen. So this is our attempt to helping students see that, for example, in this particular structure, there is only one axial hydrogen that can be removed by the base, right? And practically there is only one place for that elimination or the double bond to form, right? So this is one aspect. Here I only have a screenshot. I wanted to position the molecule in the reactive conformation. I mean, there is quite a few things that we could improve when it comes to molecular, but then I'll share those with you at the very end, which is, it's going to be not this slide, but the slide after. And this is where, we wanted to basically impress our students with how complex an organic molecule it can be. And doxorubicin was the example we chose because it's medically very, very relevant, and it's also very functionalized. I mean, this is a screenshot that I took just, So this was a way of for us to awe our students when it comes to what organic chemistry can look like. And we talk about doxorubicin in the context of acids and bases a little bit. And so this is, these are some of the applications of the app. When it comes to what I would like the app to do in the future, rotation about CC bonds would be a good thing. So then, students can actually do in the app what they basically do with the molecular model. If they forget their molecular model kit, if they don't want to use it, it would be, a way for those two to complement each other or replace each other. I talked to Julia about the possibility of flipping the chair in a cyclohexane, and she says that's doable, an animation type of thing. She knows more about how that is if that is possible, or about how that is to be done. But she said it's possible, so I'm really excited about that opportunity. And this idea of superimposability, if possible, to take two structures, to play with them in the app to see, what makes them superimposable or not superimposable. So clarify that, limit that line, that border between different types of stereoisomers, in antio, diastereo, and meso compound. So these are some of my wishes. And I don't have a last slide, but I would like to, I'm grateful, to be honest, for the opportunity of being here and sharing this with you. I'm grateful to Scott for sharing the app with me and with us, with the 231 teaching team. And I'm grateful to you for coming here today and listening to us. Thank you very much. And we're here to answer all of your questions. Okay, so I see Steve, please go ahead. You raised your hand.
Sure. Thanks, Violetta. Thanks, Scott. So this all looks very cool, obviously, and I agree that the fundamental issue of putting something manipulable and three-dimensional, or at least the illusion of three-dimensional, into students' hands or on their screens is hugely valuable. I can do all this with a web page in JS mode. So I can, create a little spinning object on a web page, and I can send a QR code to it, and they can grab it and move it around if they want. Have you looked at, or are you aware of any studies that looked at the different ways to do this, in either in terms of ease of use and student preference, or hey, we're educators, actually which type of technology is better at helping students understand all of these concepts? Is a web page better? Is a VR better? Are those things in combination with a two-dimensional drawing better? Do you know if anybody's looked at that kind of thing? Because there are obviously different opportunities and different choices for people who want to do this, to explore what's the best one to use.
Yeah, I mean, I think these are technologies at all sorts of different levels of maturity. So I think that, it's a great idea, Steve. I think that I would be really interested, especially in the light of the fact that a lot of the students in the feedback about molecular asked for exactly what you're talking about. And so my feeling is that it's probably the case that if you can provide them with a smorgasbord of different options where they can pick and choose the thing that they find most helpful, and that could be a physical model, it could be the textbook is just fine for them, it could be like a library of interactable structures that are not in augmented reality, it could be augmented reality.
Right.
You do then run into the, you don't want to sort of offer them too much choice, because then you get paralysis of choice as well. I think it's a great open question, and my guess is that if you asked a class full of students, you'd get a really big range of answers in terms of their preference. I'm not aware of whether anyone has done a straight comparison of this tool versus that tool. That's always a tricky one to do, because a lot of surveying students is really fraught, and I often worry when we survey that we can inject so much bias into that survey by how we ask the questions and how enthusiastic we sound about a particular thing. I think I would be a terrible person to survey the students about which technique they thought was good, because I'd be obviously buzzing about the one that I had some involvement with, right? But I think it's a great idea for a research project. Someone should definitely, compare a bunch of these tools, and this is by no means the only augmented reality molecular visualization tool out there, and sort of see which is the best. I would love to read that thing.
Should we be that someone, Scott? Is that?
Yeah,
I,
if by we you mean you, yes.
I guess one quick follow-up. Can you give me an idea, a sense of the workflow? If I gave you an MLO file that you'd never seen before, or a PDB protein structure file that you'd never seen before, or something that gave you the topology of a molecular orbital you'd never seen before, how long does it take you before you give me the QR code that puts it on my phone?
Yeah, so Julia can do that quite quickly. Like the development that we're going to do on the app this year is basically to try and figure out to what extent we can automate that process.
Okay.
So, you could send it and then like ideally you'd have a website where you could like upload, the thing you're interested in visualizing.
And it would just do it. And
That's right, yeah.
Yeah.
But I think we're a little ways away from that yet. Like, Julia is still, doing things behind the scenes to enable this to happen in a way that, like, she hasn't taught us how to do it yet. But part of the process, part of the process is going to be to make this sustainable. We obviously need exactly the feature, right?
If I can add something to Steve's first question. So in terms of, what's out there, I was trying to screen through the literature and come up with a conclusion. Like I know other people develop their own version of augmented reality apps, but they all seem to target a certain concept, mostly stereoisomerism. And they tied it to a certain, activity, like a teaching activity. And ultimately, my take on this was that the tool worked, the students liked it, they enjoyed it, they seemed it helped them, but their performance didn't change as a result of using it.
right.
So I think with these tools, what the benefit is that the student has the option. And in the survey, I saw quite a few of them saying that, the molecular models and the app, they complemented each other. So I think it's more a matter of, here is another way for you to look at these things. And the more of these structures they have, the more likely maybe they are to go engage with them. Yeah, so that's my take on what happens on that, but there is a lot happening out there.
Thank you.
Yeah, I think in general, doing some sort of teaching innovation that is a small part of a single class in a course. Well, I guess molecular gets spread over multiple classes. But it's just like a different modality of interacting with the same material. It's very hard to demonstrate that what effect that has on student performance. I'm just deeply skeptical of studies which show transformative results, because it's just too easy to put your finger on the scale and give them a slightly easier exam question, and then it would look like they suddenly got much better. So doing this in a perfectly fair way is really, really hard. And honestly, I think that if you're doing something, you're showing the students material in a way that you are enthusiastic about, the students will reflect that enthusiasm. I think it's so, I think that using a technique that you find it easiest to explain a concept with is probably the right thing to do. But also making sure that they have these other modalities that they can use if that explanation wasn't the best possible one. Violetta, I had not seen the 231 examples, so it was actually really fun to see them, especially sort of the bigger molecules are neat in the sense that you can like just fly through them with your phone, which is a pretty fun.
Yeah, I had fun showing it to them and showing them the flat portion of it, because I don't know if at times when I teach, I say these two faces are equally accessible, so that's why we get a racemic mixture, but they are like, well, so it's interesting to build the structure so they can actually see why certain portions of a molecule are more reactive than others, from a steric perspective. So there are multiple things that get me excited about this possibility, and hopefully, as you mentioned, that will translate into student engagement. So what I've seen in the literature is that these types of tools, they engage students, they motivate them, they like it, they have fun, but ultimately their performance doesn't seem to be affected by their response to the tool.
Right.
Yeah.
I mean, Steve, I remember you talking to us last year and sort of showing like more dramatic changes to courses really could have an effect on student performance, right? But I think that's a more sort of wholesale change of the entire course structure rather than sort of like a little innovation.
Yeah, I would hesitate to say that I've been able to draw any direct cause effect link between any one particular thing we did and those results. Because we changed so many things in concert with each other, and because the new course framework we developed was really integrating all of those things together.
Right.
You as you said, you can do little individual surveys, and we've found a lot of value in directly asking students, hey, do you think this was helpful to you? But obviously there can and it always will be disconnects between students' understanding of how something might have helped or what their performance is going to be and what it actually is. And so yeah, like you say, it's difficult to draw I think specific cause effect conclusions in that. You can run little workshops, and you can run little tiny events where you ask somebody some questions and then you let them play around with a new learning resource for a while, and then you ask them those questions again and you see how much they learned and you compare that to another set of stuff. But that's an artificial environment, that's an artificial space where you're measuring that. And that doesn't necessarily tell you whether they remember anything that they were supposed to have learned when they're taking a course 2 years from now. So yeah, there are always caveats with that kind of thing. I'd be curious to see. I think you're right. Automating the back end is critical. I can make little web pages and I can put little spinny protein molecules on them all day, but if no one else knows how to do that, it's not going to be a widely useful educational resource. And this all looks great, but if I want to animate a particular reaction coordinate to a particular reaction and I have no idea how to do it, how to create the code that does this, then it's a dead end. So yeah, finding a way to automate the system so that it generates it, and then presumably this, like the structure information has to be stored on a server somewhere. That server has to be publicly accessible. Someone has to pay for that. I mean, I assume you're just throwing all this on a computer in Victoria somewhere and hoping nobody notices.
Yeah, no, I mean the advantage is that making an app and making it a free app, like all that information is essentially stored by Apple for us. So we're not like we have to pay like a developer license for the app, but that's a relatively small amount of money, like the amount of money that we can totally justify spending every year, $75 a year or something. So it's not a huge amount of money. There's no like ongoing maintenance. So once we have made a particular depiction, it'll always be there and it'll always be available. But I agree with you about the sort of ongoing development for sure.
Amanda has a question. Sorry. Amanda, would you like to ask your question?
I mean, I'm good. I don't know if I had anything raised, but this is awesome. Oh, other Amanda, good. Yeah, I was like,
Sorry, I had to be unmuted. So you can hear me now?
Yes.
Okay. Yeah, so this is really amazing. I love the simplicity of this app. And I have a question, which is, I saw it's developed in Unity. And is it possible to, I know your whole thing was the augmented reality, but is it possible to have these Unity objects and bring them into Unity for virtual reality?
I mean, I suspect so, because that's Julia's background. Like her development of the virtual reality stuff was all in Unity. And then she just translated that into augmented reality, which she had to do a little bit of reading about to figure out how that worked. So yes, I think so.
Okay.
And of course, virtual reality is like a level of immersion that is an order of magnitude or two higher than augmented reality. Augmented reality is kind of like a tweak, whereas virtual reality is like boom.
Totally.
But of course, the accessibility is different, right? Like I can, if I poll my students, literally 99.5% of them have a smartphone. I haven't tried polling them about a virtual reality device, but I imagine it's maybe single figures.
Yeah. I'm asking almost for my own interest because I have a student who's trying to work on a project and we want to study something in VR, but we're not actually interested in developing the VR ourselves. And then my student's just been running into so many issues with like what's available in the Unity library. So I'll follow up with an email with you because it's just surprisingly hard to find something like this to just bring into Unity and play with yourself.
Right.
So this has got me really excited to see this.
Okay, yeah, great. Like I can definitely put you in touch with Julia, and I think she would be able to answer questions.
Awesome, thank you.
And Steve knows a guy. What does he do there, Steve?
The answer to that question seems to change every 3 months, and every time he tries to explain it to me, I get lost again. He leads various teams to develop various new exciting things all the time.
Right.
But he's also very familiar with technical back-end stuff. So Amanda, if you've got specific questions about, I'd like to add more things to a library somehow, is there a way that I can do that? He might not know, but he probably can point you in a direction to get some insider info, or if there's some new element or new capability that you'd like to see developed. I've got it in. We can deliver that message that might work its way to the correct team.
I think I'll be exploiting that in at some stage, Steve. So thanks for
You'll have to come back to Kelowna and we can arrange a lunch in a month that you're actually here.
Done.
Looks like we're done. Thank you everybody for coming. Okay, it was great to see some of you and see your names at least. That's it for today. I wish everybody a great day and a very happy new year.
Thanks,
Thank you
everyone.
for coming.
Bye.
Bye-bye.